Let's see example 4. A long coaxial capacitor with a length L, as shown in figure Q4, consists of conductor plates at R equal to 2 cm and R equal to 4 cm. The outer conductor plate is said to be Hertz, while the potential for inner conductor is 24 volt. Given that the relative permittivity for dielectric 1, which is between R equal to 2 cm and 3 cm, is given by epsilon R1 equal to 2.5, while relative permittivity for dielectric 2, which is between R equal to 3 cm and 4 cm, is epsilon R2 equal to 4.6. The question is, we have to determine A. Potential in dielectric 1 and dielectric 2. State all the assumption made. Second, E and D in dielectric 1 and dielectric 2. Next question, total charge on the inner plate capacitor, which is at R equal to 2 cm. And lastly, capacitance of the structures. So this is the figure. So imagine you have a long coaxial capacitor. We have conductor at R equal to 2 cm and R equal to 4 cm. Between these two conductors, we have dielectric material. But here we have two-layer dielectric material, which is between 2 and 3 cm is a material which epsilon R1 equal to 2.5. And between 3 and 4, we have another material which have the relative permittivity epsilon R2 equal to 4.6. Then, the conductor at R equal to 2 cm is set to be 24 volt, while the outer conductor is grounded. That is the situation. So, how can we solve the problem related to this kind of structures? First of all, you have to know that this kind of structures is cylinder, so you have to use cylindrical coordinate. For the solutions, we have to use cylindrical coordinate for Laplacians. When we refer to the table of Laplacian, we will see that we have three components, which is R component, phi component, as well as Z components. Therefore, we have to use the R component because when we see our structures, the potential is depend on the R components. So, we take the R component for Laplacian. So, here we have the Laplacian of V equal to 1 over R, del over the R, in bracket 1 del V over the R is equal to 0. Here, we assume that rho V inside both dielectric is equal to 0. Because we have the right hand side is rho V divided by epsilon. When rho V equal to 0, so this equation become the homogeneous equations, or we call as a Laplacian equations. So we have to analyze two regions, which is in dielectric 1 between 2 cm and 3 cm. And here we have the V1. So the Laplacian should be analyzed for V1. So we have Laplacian of V1 equal to 1 over R del over the R del V1 over del R equal to 0. So we have to bring R to the right hand side. So it's equal to 0. And then we have to integrate both sides. So we get here that the integration of 0 is equal to a constant. We rename as A. So we have R dV1 over dr equal to A. And then we have to bring R here to the right hand side. So we get A over R. And then we have to make another integration. So our final solution is V1 equal to A ln R plus B. And B is another constant. Similarly, in dielectric 2 between 3 cm and 4 cm, using similar arguments, so we obtain V2 equal to C ln R plus D, where here C and D are constants. Next, we have to find the value of this constant. A, B, C, and D. How to find the constant? We have to use the boundary conditions. So we have 4 conditions here, which is the first one at R equal to 2 cm, we have V1 equal to 24 volt because we connect R equal to 2 cm with 24 volt. And then at R equal to 4 volt, we connect to ground. So at R equal to 4 cm, so this is for V2, V2 equal to 0 volt. And the third condition, at R equal to 3 cm, which is at the boundary between dielectric 1 and dielectric 2. So the potential is the same, which is V1 equal to V2. And at the same place, at R equal to 3 cm, so our D is the same, which is D1 normal is equal to D2 normal, with our assumption that rho s equal to 0 at the boundary. So D1 normal equal to D2 normal, where D is equal to epsilon at E. So D1 normal equal to epsilon 1 E1 normal equal to epsilon 2 E2 normal. This is 4 conditions that we use to find A, B, C, and D. From A, V1 equal to A ln R plus B and V2 equal to C ln R plus D. When we change R equal to 2 cm or 0.02 meter, we get here V1 equal to A ln 0.02 plus B equal to 24 volts. From here, we can rearrange where B equal to 24 minus A ln 0.02. This is the first equation. And then, at R equal to 4 cm or 0.04 meters, we have V2 equal to C ln 0.04 plus D is equal to 0 because this is ground. From here, we can rearrange where we get D is equal to minus C ln 0.04. This is the second equation. Next, at R equal to 3 cm or 0.03 meter, we have V1 equal to V2. Okay, V1 in a region 1, V2 in a region 2. At this boundary, A ln 0.03 plus B, this is from equation 1, is equal to C ln 0.03 plus D. This is from equation 2. So we use the same R. So we have to substitute equation 1 and equation 2 into equation 3. We have A ln 0.03 plus 24 minus A ln 0.02 equal to C ln 0.03 minus C ln 0.04. And when we solve this expression, we get A ln 1.5 plus 24 equal to C ln 0.75. This is our fourth equation. Alright, at R equal to 3 cm or 0.03 meter, we have another rule which is D1 normal equal to D2 normals, where because we know that D equal to epsilon E, so D1 normal equal to epsilon 1 E1 normal, while for D2 normal equal to epsilon 2 E2 normals. We can find E1 and E2 using gradients, the gradient of V. So E equal to negative gradient V. So for E1 we have negative gradient V1, for E2 we have negative gradient V2. So the gradient V1 and V2 we get here A divided by R, and for V2 C divided by R. So we have to rearrange the expressions. So we have finally A equal to epsilon 2 divided by epsilon 1 C. From the equation we know that epsilon R2 equal to 4.6 while epsilon R1 equal to 2.4. So we have to substitute into these expressions. Epsilon 2 equal to epsilon R2 epsilon naught, while epsilon 1 equal to epsilon R1 epsilon naught. And then here we can cancel out epsilon naught, so our expression become A equal to 1.84 C. This is our fifth equation. Then we have to substitute equation 5 into equation 4. So what we obtain here, 1.84 C ln 1.5 plus 24 equal to C ln 0.75. And then we rearrange, and finally we obtain C equal to negative 23.21. And we have to change the C into equation 5, equation 1, and equation D. And later on, you will get A equal to minus 42.72, B equal to minus 143.12, and lastly, D equal to minus 74.71. So now we get all the constant that we need. Finally, we have to put the constant into our original equation, which is V1 equal to A ln R plus B, or equal to minus 42.72 ln R minus 143.12 volts, while V2 equal to C ln R plus D equal to minus 23.21 ln R minus 74.71 volt. For the next question, find E and D. Okay, we need to use gradients, because now we know what is the V1 and V2. So from there, we can obtain what is the E1 and D1 later on by using gradient. So we have two regions, which is dielectric 1 and dielectric 2. In dielectric 1, we have E1 equal to negative gradient of V1 equal to negative, and then we have another negative 42.72 divided by R and direction of R. So we obtain here E1 equal to 42.72 divided by R in direction of R volt per meter. And then D1 equal to epsilon 1 E1. So epsilon 1 equal to 2.5 epsilon naught. Later on, you get D1 equal to 106.8 epsilon naught divided by R in direction of R coulomb per meter. Similarly, in dielectric 2, we have to use gradient for V2. Now, you will obtain E2 equal to 23.21 divided by R in direction of R volt per meter. And similarly, D2 equal to epsilon 2 E2, while E2 equal to 4.6 epsilon naught. Substitute everything, and your final answer will be 106.78 epsilon naught divided by R in the direction of R coulomb per meter squared. So this is a step-by-step that you need to find the electric field intensity as well as electric flux density in dielectric 1 and dielectric 2. For question C, find the total charge at R equal to 2 cm. So we have to use Gauss law, where Q equal to the integration of d dot ds. Since at dielectric 1, therefore we use d equal to d1. So Q is basically on the surface of the side cylinder. So we have to choose the correct coordinate system, the correct surface. So here we have d dot ds, our d equal to 106.8 epsilon naught divided by R, and our ds for the side surface of cylinder is equal to R d phi dz in direction of R, where R in this case equal to 0.02 meter. So you have to solve these integrations. We can see here that the R component can cancel out. Right, so here we have 106.8 epsilon naught, and then we have the integration into dz from 0 to L, the length of the cylinder, and then we have d phi from 0 to 2 pi. And then the final solution for Q is equal to 108.83 L picocoulomb. Because we don't know in this case what is L. Lastly, for capacitance of the structures. Capacitance equal to the ratio of charge divided by voltage. So the charge at R equal to 0.02 meter equal to 118.83 L picocoulomb, and our potential at R equal to 0.02 meter equal to 24 volts. So our final solution will become 4.95 L picofarad. So that's the solutions.